What if I told you that the emptiest space in the universe isn't empty at all? That what we call a vacuum, a void where nothing seems to exist, is actually a bubbling, seething ocean of invisible activity. This is the quantum vacuum, one of the most baffling and beautiful frontiers of modern physics. Beneath the surface of what looks like nothingness lies a hidden world where particles pop in and out of existence, where energy fluctuates in ways that defy common sense, and where the very fabric of reality behaves in ways that still leave scientists speechless. Think of it like this. Imagine standing on the shore of what appears to be a perfectly still lake. From a distance, the water seems calm, motionless. But if you lean closer, you'd see it's actually teeming with life, tiny ripples, unseen currents, flashes of movement too subtle to catch at first glance. That's the quantum vacuum. It's not the void we once imagined, but a dynamic, almost alive medium where the rules of the universe are rewritten every fraction of a second. This is where particles and antiparticles dance in and out of existence, where energy borrows from the future to pay the past, a place so strange that even Einstein struggled to wrap his mind around it. And here's the thing, this isn't just some abstract theory. The quantum vacuum holds the keys to some of the biggest mysteries in science. It's the engine behind dark energy, the force pushing the universe apart faster and faster. It might even hold clues to parallel realities, wormholes, or the origin of everything we know. Over the next while, we're going to dive into 30 of its most mind-bending secrets, phenomena that challenge our understanding of space, time, and existence itself. So if you've ever wondered what truly lies beneath the surface of reality, get ready, because what we're about to explore will change how you see the universe and the very meaning of nothing forever. The first mystery of the quantum vacuum is also one of the most frustrating because it defies everything we think we know about energy. Even in the deepest void of space, where no stars shine and no particles drift, there's still an unfathomable amount of energy humming beneath the surface. Scientists call it zero-point energy, and it's not just a tiny flicker. It's infinite, that's right. According to quantum field theory, every cubic centimeter of empty space contains more energy than all the matter in the observable universe combined. So why can't we plug into this cosmic power grid? The answer lies in the bizarre rules of the quantum world. Zero-point energy isn't like a battery you can drain. It's more like an ocean where the waves never stop. Particles and antiparticles flicker in and out of existence so fast that their energy averages out to zero. But here's the catch, their fleeting presence still leaves ripples in reality, and we've actually seen proof of this. Take the Casimir effect, where two metal plates placed incredibly close together in a vacuum get pushed toward each other. Why? Because the space between them is too narrow for certain quantum fluctuations to fit, while the outside still buzzes with activity. The result, a measurable force proof that the vacuum isn't empty at all. Yet harnessing this energy remains a dream. The universe balances its books too perfectly. Every burst of energy borrowed from the vacuum must be paid back almost instantly. It's like trying to catch smoke with your hands. Even if we could tap into zero-point energy, controlling it would mean rewriting the laws of physics as we know them. Some theories suggest wormholes or warp drives might one day unlock its potential, but for now, this infinite energy source remains just out of reach, a tantalizing reminder that the universe keeps its deepest secrets hidden in plain sight. Now let's dive into the second strangest quirk of the quantum vacuum. The phantom particles that shouldn't exist. Imagine flipping a coin, and for the briefest instant before it lands, both heads and tails flash into reality at once. That's roughly what happens when virtual particles, pairs of matter and antimatter, spontaneously erupt from the void. Heisenberg's uncertainty principle lets these particles cheat the universe's energy ledger, borrowing energy just long enough to exist before vanishing back into the vacuum. It's like cosmic sleight of hand, where the rules of classical physics take a coffee break. Here's where it gets weirder. These particles aren't just hypothetical, they leave fingerprints everywhere. Quantum fluctuations slightly shift the electrons orbiting atoms, an effect measurable with lasers. Even empty space glows faintly at absolute zero because of them, a phenomenon called vacuum polarization. But the ultimate proof came from black holes, when Stephen Hawking realized virtual particles could be ripped apart near an event horizon, one falling in while the other escapes as real radiation. It revolutionized astrophysics. Suddenly, black holes weren't eternal traps but slowly evaporating objects, thanks to the vacuum's restless activity. Yet the implications go deeper. If particles can materialize from nothing, does that mean nothing is a misnomer? Some theories suggest the vacuum is a sort of cosmic loom, weaving the fabric of space-time itself from these fleeting fluctuations. Others wonder if entire universes could bubble up the same way. It's a dizzying thought that existence might be less like a solid stage and more like a froth of possibilities popping in and out of focus. The quantum vacuum doesn't just challenge physics, it forces us to rethink what reality even means. The third mystery of the quantum vacuum is so colossal it makes other cosmic puzzles seem trivial. It's called the cosmological constant problem, and it's the sharpest thorn in the side of modern physics. Here's the issue: when we calculate how much energy the quantum vacuum should contain, the numbers spiral into absurdity. The vacuum's predicted energy density is 10 to the power of 120 times larger than what we actually observe, a discrepancy so vast it's like predicting an ocean and finding a single drop. This isn't just a rounding error, it's the greatest mismatch between theory and observation in all of science. The vacuum's energy should curve space-time so intensely that the universe would either rip itself apart or collapse instantly. Yet here we are, with galaxies gently drifting apart. How can reality be so wildly off from our calculations? The answer might rewrite our understanding of everything. Enter dark energy, the mysterious force accelerating the universe's expansion. Its measured strength aligns eerily with the tiny sliver of vacuum energy we detect. Coincidence, or is the vacuum subtly shaping cosmic destiny? Some physicists think dark energy is vacuum energy, just diluted by some unknown mechanism. Others propose undiscovered symmetries or extra dimensions cancelling out most of the vacuum's power. A wilder idea suggests multiple universes with randomly varying constants. We just happen to live in one where the numbers barely allow existence. The stakes couldn't be higher. If the vacuum's energy was slightly stronger, stars and galaxies never would have formed. Slightly weaker, and gravity would have crushed the cosmos long ago. This razor-thin balance hints that we're missing something profound, a hidden principle taming the vacuum's fury. Solving this riddle might reveal whether the universe expands forever, collapses, or tears apart in a big rip. The quantum vacuum isn't just an abstract curiosity, it holds the blueprint of reality's fate, and right now that blueprint reads like a paradox written in vanishing ink. But what if the quantum vacuum isn't just strange, what if it's unstable? This brings us to the fourth mystery, and it's the stuff of cosmic nightmares. Imagine our universe's vacuum isn't the true lowest energy state, but a temporary plateau, a false vacuum. Like a marble resting on a hill, it seems stable, but one nudge could send it tumbling into a deeper, darker valley of reality. If that happened, a bubble of true vacuum could form, expanding at the speed of light, rewriting the laws of physics as it goes. Stars, planets, even atoms would unravel in an instant, replaced by something utterly alien. The culprit here is the Higgs field, the same one that gives particles their mass. Right now, it's sitting at a certain energy level like a frozen lake. But some calculations suggest that under extreme conditions, say, inside a super collider or near a dying star, it might suddenly drop to a lower state, releasing catastrophic energy. The terrifying part, we wouldn't see it coming. A single quantum event could trigger this decay anywhere in the universe, and by the time the bubble reached us, it would already be too late. Yet there's a sliver of hope. The fact that the universe has lasted billions of years suggests the vacuum is probably stable, or at least on a timescale so vast it's unlikely to collapse in our cosmic neighborhood. But probably isn't the same as definitely. Some theories argue that the Higgs field is already in its true state, meaning we're safe. Others point out that if vacuum decay were possible, it might have already happened somewhere else in the multiverse, leaving us in a fortunate bubble of survivable physics. Either way, this isn't just theoretical doom-scrolling. Understanding vacuum stability is key to unlocking deeper truths about the Higgs field, the early universe, and even the possibility of other, stranger realities lurking beyond our own. The quantum vacuum isn't just a curiosity. It might be the most delicate house of cards in existence, holding up everything we know, and whether it stands or falls could depend on laws we're only beginning to glimpse. Here's something that will bend your perception of reality. Empty space isn't the same for everyone. If you're floating motionless in the void, you'll see nothing but darkness, a perfect vacuum. But if you suddenly accelerate, something bizarre happens. The empty space around you bursts into a glow of heat and particles, as if the universe itself is resisting your motion. This is the Unpack effect, a phenomenon where acceleration conjures particles from nothingness, proving yet again that the quantum vacuum is anything but empty. The science behind this is as beautiful as it is mind-bending. According to Einstein's relativity, motion is relative. There's no universal standstill. So when you accelerate, your perspective shifts dramatically. The quantum fields that appear calm to a stationary observer now look like a seething storm of particles to you. These aren't illusions, they're real particles with real energy, radiating heat as if you're surfing through a cosmic sauna. The faster you accelerate, the hotter it gets. For a human, the effect is far too weak to detect. You'd need to accelerate at 1 trillion times Earth's gravity just to feel a whisper of warmth. But near a black hole's event horizon, where gravity creates extreme acceleration, the Unpack effect becomes impossible to ignore. This is where things get even stranger. The Unpack effect ties directly into Hawking radiation, the glow emitted by black holes. Just as acceleration makes particles appear in empty space, a black hole's monstrous gravity does the same at its event horizon. From the outside, it looks like radiation slowly leaking away the black hole's mass, but from the perspective of someone falling in, nothing but darkness. It's the same phenomenon viewed from two wildly different angles, revealing how deeply motion and gravity are woven into the fabric of quantum reality. And then there's quantum friction, an eerie consequence of this cosmic dance. Imagine two mirrors placed in a vacuum, perfectly still. Normally, they'd feel no force between them. But if one mirror starts accelerating, the Unpack effect kicks in, creating a drag force as if space itself is thickening around it. This isn't just theoretical, it's a measurable prediction of quantum field theory, showing how motion through the vacuum isn't smooth but bumpy, like wading through an invisible quantum molasses. So what does this all mean? The Unpack effect blurs the line between particles and perception, proving that what we call reality depends entirely on how we're moving through it. It hints at a universe where existence itself is a kind of mirage, shaped by acceleration and gravity. And if that's true, then the quantum vacuum isn't just a backdrop for the cosmos, it's an active participant, responding to every twist and turn of motion with a flicker of particles, a pulse of heat, and a whisper of the deepest secrets of spacetime. Picture two coins flipped on opposite sides of the universe, yet somehow, when one lands heads, the other instantly shows tails, no matter the distance. This isn't magic, it's quantum entanglement, and the vacuum is the invisible stage where this cosmic choreography plays out. known as the EPR paradox after Einstein, Podolsky, and Rosen, who first highlighted its absurdity. Entanglement forces particles to mirror each other's states faster than light could travel between them. Einstein called it spooky action at a distance, convinced it revealed a flaw in quantum theory, but the vacuum had other plans. Here's how it works. When particles become entangled, often through interactions in the vacuum's fluctuating fields, their properties lock together like synchronized dancers. Measure one's spin or polarization, and its partner snaps into the opposite state, even if separated by galaxies. The vacuum isn't just empty space here, it's the medium that preserves this eerie connection, like an invisible thread woven into space-time itself. For decades, physicists argued over whether hidden variables, secret rules governing the particles, could explain the effect. Then came Bell's theorem, a mathematical bombshell proving that no local hidden variables could account for entanglement's precision. The vacuum's role wasn't just passive, it was enabling a fundamental weirdness that defied classical intuition. Recent experiments have crushed all remaining skepticism. Loophole-free Bell tests conducted with atoms separated by over 1,000 kilometers confirm entanglement's reality. Photons fired through fiber optic cables or beamed via satellite sync their states with flawless accuracy, their connection mediated by the vacuum's quantum fields. Even more startling, entanglement isn't rare. The vacuum constantly spawns entangled particle pairs, linking them across space before they vanish back into the void. Some theories suggest the entire universe might have been born from a vast quantum entanglement event, with the vacuum acting as the primordial glue. But the real shocker is what this means for reality itself. If entanglement holds, information seems to bypass the speed of light, violating relativity's core principle. Yet the vacuum cleverly sidesteps the paradox. No energy or matter travels between the particles. Their correlation is baked into the fabric of existence from the start. It's as if the universe cheated by preloading the outcome, with the vacuum serving as the ultimate referee. This isn't just a quirk of tiny particles, it's the foundation for quantum computing, secure communication, and maybe even the structure of spacetime. The vacuum doesn't just host entanglement, it might be the reason reality stays stitched together at all. What if the vacuum of space wasn't just an invisible stage for quantum fluctuations, but a frictionless river flowing without resistance? This is the radical idea behind the superfluid vacuum theory, a concept that reimagines the fabric of reality as a cosmic liquid more exotic than anything in nature. Picture helium cooled to near absolute zero, where it defies gravity, climbs walls, and never slows down. Now imagine that same eerie behavior, but applied to the entire universe. The math behind this is staggering. Superfluids like those created in labs have zero viscosity, meaning they flow without losing energy. Apply that to the vacuum and suddenly, the quirks of quantum mechanics start to make eerie sense. Particles could be like ripples in this fluid, their properties determined by how they interact with its flow. Even spacetime itself might emerge from the whirls and eddies of this underlying medium. It's a vision where the universe isn't built on static emptiness, but on a dynamic, liquid-like essence, one that might explain why quantum particles behave so strangely. Neutron stars offer a tantalizing hint this isn't just fantasy. These ultra-dense corpses of dead stars are thought to contain cores of superfluid neutrons spinning frictionlessly for millennia. If matter under such extreme conditions can become a superfluid, why not the vacuum itself? Experiments with Bose-Einstein condensates ultra-cold gases that mimic superfluid behavior show how collective quantum effects can create emergent properties far weirder than their parts. The vacuum might be the ultimate example of this, a system where trillions of quantum interactions give rise to the illusion of empty space, but the implications go deeper. If the vacuum is a superfluid, it could redefine our understanding of motion. In a frictionless cosmos, inertia, the resistance to acceleration might not be fundamental but a side effect of how objects interact with this hidden medium. Some theories even suggest that the vacuum's superfluid properties could be the key to unifying gravity with quantum mechanics, treating space-time not as a static grid but as a flowing, ever-changing quantum liquid. Of course, not all physicists are convinced. Critics point out that superfluids require extremely low temperatures, while the vacuum exists everywhere, even near blazing stars. Yet proponents argue that the quantum vacuum's temperature isn't the same as the thermal energy we're familiar with. Its fluctuations might already mirror the chaotic yet coherent motions of a superfluid, just on scales we're only beginning to probe. Whether this theory holds or not, it forces us to confront a haunting possibility that the universe's deepest layers aren't just mysterious, they're fluid, alive, and stranger than any sci-fi. The vacuum might not be the void we once imagined, but a boundless, frictionless sea shaping reality in ways we're only starting to navigate. And if that's true, then every particle, every force, even the flow of time itself, could be little more than waves on its invisible surface. Some of the most heated debates in modern physics swirl around a single, terrifying question: what happens to information that falls into a black hole? At first glance, the answer seems obvious. Nothing escapes a black hole's gravitational grip, not even light. But when you factor in the quantum vacuum, the story unravels into one of science's greatest paradoxes. Stephen Hawking stunned the world when he calculated that black holes aren't completely black, they slowly leak radiation, thanks to the vacuum's restless particle-antiparticle dance near the event horizon. Over eons, this Hawking radiation causes black holes to evaporate, vanishing into nothingness. Here's the crisis: if a black hole disappears, what happens to all the information about the stars, planets, or spaceships it swallowed? Quantum mechanics insists that information can never be truly destroyed. It might be scrambled, but it should still exist in some form. Yet Hawking's equations suggested the opposite, showing radiation as random noise, carrying no trace of what fell in. This contradiction, known as the black hole information paradox, pits quantum theory against general relativity in a battle with no clear winner. The vacuum isn't just a bystander here, it's the stage for the conflict. One proposed solution, the firewall paradox, argues that the event horizon isn't the smooth gateway relativity predicts, but a searing wall of energy created by quantum effects ripping apart entangled particles. Picture an astronaut crossing the horizon. Instead of drifting gently into oblivion, they'd hit a literal firewall, incinerated by the vacuum's fury. This idea is as controversial as it is dramatic, with critics pointing out it violates Einstein's equivalence principle, the bedrock of relativity. Then there's the holographic principle, a mind-bending twist that reimagines the vacuum's role entirely. It suggests that all the information inside a black hole isn't lost but encoded on its surface, like a cosmic QR code. The vacuum fluctuations at the horizon might act as a projector, translating three-dimensional reality into two-dimensional data. If true, the universe itself could be a hologram, with the quantum vacuum serving as the ultimate storage device. Recent breakthroughs add fuel to the fire. Simulations using quantum computers hint that information might escape black holes after all, woven into Hawking radiation's subtle patterns. Meanwhile, studies of wormholes, hypothetical tunnels through space-time, suggest entangled particles could form bridges, preserving information in ways we're only starting to glimpse. The vacuum, it seems, is playing a deeper game than anyone suspected, hiding answers in the quantum fine print. What's at stake isn't just academic. If information can vanish forever, our understanding of reality is flawed at a fundamental level. But if it persists, hidden in the vacuum's quantum knots, we might be staring at the key to unifying gravity and quantum mechanics. The black hole paradox isn't just about collapsed stars. It's a puzzle that could rewrite the rules of existence itself. proving once again that the emptiest places in the universe hold the most explosive secrets. One of the most astonishing gifts from the quantum vacuum isn't happening now, it happened in the first sliver of a second after the Big Bang. Scientists call it cosmic inflation, a period when the universe expanded faster than light itself, stretching from smaller than an atom to nearly its current size in less time than it takes light to cross a single proton. And the driving force behind this explosive growth, the vacuum's own energy, acting like a cosmic accelerator pedal pressed to the floor. But here's where it gets even wilder. Inflation didn't just stretch space, it amplified the vacuum's quantum fluctuations, turning microscopic ripples into the seeds of galaxies. Imagine blowing up a balloon with tiny wrinkles on its surface. As the balloon inflates, those wrinkles stretch into massive ridges and valleys. That's exactly what happened to the early universe. The quantum jitters of the vacuum, random variations in energy at the smallest scales, were stretched so dramatically that they became the gravitational wells where matter would later clump, forming stars, galaxies, and the vast cosmic web we see today. The proof is etched into the oldest light in the universe, the cosmic microwave background, or CMB. This faint glow, left over from when the cosmos was just 380,000 years old, shows temperature variations that match the vacuum's primordial fluctuations with stunning precision. Warmer spots, regions where denser quantum ripples seeded future galaxy clusters. Cooler spots, the cosmic valleys where less matter pooled. These fingerprints are so precise that they've turned inflation from a bold hypothesis into the leading explanation for our universe's structure. Yet the implications go far beyond our own cosmic neighborhood. If inflation was driven by the vacuum's energy, could it still be happening elsewhere? Some theories suggest that inflation isn't a one-time event but an eternal process, with new universes constantly bubbling up from the quantum foam like bubbles in an infinite champagne glass. Each would have its own unique physics, its own constants, its own version of reality, all sprouting from the same vacuum that birthed ours. This idea, known as the multiverse, is controversial but impossible to ignore. If true, it means our universe isn't special, just one accidental garden in a sprawling wilderness of cosmic possibilities. The vacuum's fluctuations didn't just shape our world, they might have spawned countless others, each forever hidden beyond the horizon of our observable space. And here's the haunting twist. If other inflationary bubbles exist, they could be colliding with ours right now. Theoretically, these collisions would leave scars in the CMB circular patterns of temperature variation where the boundaries of universes brushed against each other. Astronomers have searched for these signatures, though none have been confirmed yet. But if they're out there, it would be direct evidence that our universe is just one page in an infinitely thick book written by the quantum vacuum. Whether inflation happened once or continues eternally, one thing is clear: the vacuum isn't just the backdrop of reality. It's the architect, the sculptor, the hidden hand that shaped everything from the largest galaxy to the smallest atom. And if its energy could ignite a runaway expansion once, who's to say it won't, or hasn't already happened again? The universe we know might just be a single eddy in an endless quantum current, with the vacuum whispering the secrets of creation in a language we're only beginning to decode. Imagine holding a perfectly still tuning fork that suddenly, inexplicably starts vibrating on its own. That's essentially what happens to electrons orbiting an atom, thanks to the quantum vacuum's restless energy. This phenomenon, called the Lamb shift, is one of the most precise validations of quantum electrodynamics ever discovered, and it all hinges on the vacuum's ability to tweak reality at the smallest scales. Here's how it works. In classical physics, an electron orbiting a hydrogen atom should follow neat, predictable energy levels like planets circling the sun. But in the 1940s, Willis Lamb and Robert Rutherford spotted something odd. Using microwave beams to probe hydrogen's structure, they found that two supposedly identical electron states had slightly different energies, a tiny discrepancy that shouldn't exist. The culprit, virtual particles erupting from the vacuum. These ghostly particles constantly buffet the electron, altering its path and energy in ways that defy Newton's clockwork universe. The numbers are staggering. The Lamb shift amounts to just 1 part in a million of the electron's total energy, like shifting a guitar string's pitch by a fraction of a hair's width. Yet this minuscule effect confirmed a revolutionary idea. Empty space isn't passive. It's a churning sea of quantum activity that physically nudges matter. Later experiments measured the shift with pinpoint accuracy, matching quantum electrodynamics predictions to 12 decimal places, making it one of the most precisely tested theories in science. But the implications go deeper. The Lamb shift isn't just a quirk of hydrogen, it's a universal fingerprint of the vacuum's influence. In heavy atoms or even exotic states like muonic hydrogen, where a muon replaces the electron, the shift grows dramatically, revealing how the vacuum's effects scale with environment. Some researchers now use these measurements to hunt for hidden particles or extra dimensions, arguing that subtle deviations from predictions could signal new physics lurking beyond our current models. What's truly remarkable is how such a tiny anomaly cracked open quantum theory's next chapter. Before Lamb, the vacuum was seen as a mathematical abstraction. Afterward, it became undeniable. The void is alive, and its whispers shape the very fabric of reality. Every atom in your body, every star in the sky, carries the faintest imprint of this quantum static, a reminder that nothing, not even the simplest hydrogen atom, escapes the vacuum's ghostly touch. Every second, light streaks through the vacuum of space at precisely 299,792,458 meters per second, a cosmic speed limit etched into the laws of physics. But what if the vacuum itself could bend that rule? Enter the Scharnhorst effect, a mind-bending prediction where light, under the strangest conditions, might briefly outpace itself. This isn't science fiction. It's a quirk of quantum fields so extreme that even causality, the unbreakable law that causes must precede effect, starts to wobble. The magic happens inside a Casimir cavity, a microscopic gap between two metal plates where the vacuum gets rewired. Normally, empty space buzzes with virtual particles popping in and out of existence. But squeeze that space tight enough, say, a few nanometers apart, and certain quantum fluctuations get squeezed out. The energy density between the plates drops below even the regular vacuums, creating a sort of negative energy corridor. In this exotic environment, photons traveling perpendicular to the plates could, in theory, gain a tiny speed boost. Not enough to send a spaceship back in time, but enough to make physicists do a double take. Here's the catch. This superluminal hopscotch only works for light of specific wavelengths that fit perfectly between the plates, and we're talking fractions of a percent faster than light, a blip so small it'd take a trip across the observable universe to notice. Even then, the effect vanishes the instant the photon leaves the cavity, snapping back to normal speed like a rubber band. But why does this matter? Because it nudges at one of relativity's sacred cows, the idea that nothing outruns light, period. The Scharnhorst effect doesn't shatter Einstein's framework. It dances on its edges, showing how the vacuum's structure can tweak the rules in ways we're only beginning to map. Some theorists argue this could hint at deeper physics, where spacetime's texture allows microscopic shortcuts or speed limits that vary by environment. Practical hurdles make testing this a nightmare. Building plates smooth and close enough to detect the effect would require nanotechnology beyond our current reach. Even if we could, quantum noise and thermal vibrations would drown out the signal. And then there's the causality problem. If information could be sent faster than light, even in this exotic setup, it might create paradoxes where signals arrive before they're sent. The universe tends to slam the door on such antics, which is likely why the Scharnhorst effect remains a tantalizing what-if rather than a lab reality. Yet the mere possibility shakes up our assumptions. It suggests that light's speed isn't just a constant, it's a negotiation between the photon and the vacuum's hidden architecture. And if the vacuum can tweak that speed under extreme conditions, what other immutable laws might be up for reinterpretation? The Scharnhorst effect doesn't just challenge our textbooks, it whispers that even the strictest cosmic rules might have loopholes if you know where to look. Even in the deepest void between galaxies, where no stars shine and matter is spread thinner than a single atom in a football stadium, space itself carries a whisper of heat. This is the quantum vacuum's temperature, a concept so counterintuitive it upends centuries of thermodynamics. We're taught that empty space should be frigid, a perfect void at absolute zero. But the vacuum defies expectations, radiating warmth not from any stars or particles, but from its own seething quantum activity. The roots of this paradox trace back to the 1970s, when physicists uncovered two startling truths. First, Stephen Hawking predicted that black holes emit radiation, now called Hawking radiation, due to quantum fluctuations near their event horizons. Far from being icy graves, black holes glow faintly, with temperatures inversely proportional to their size. A stellar mass black hole might be colder than the cosmic microwave background, but a microscopic one would sizzle at trillions of degrees, evaporating in a burst of quantum fireworks. Meanwhile, Bill Unruh showed that an accelerating observer in empty space would see a thermal bath of particles where an inertial observer sees nothing. Floor the gas pedal hard enough, and the vacuum around you transforms into a swirling soup of heat, a phenomenon now known as the Unruh effect. Both effects reveal the same deep truth: temperature isn't just about matter jiggling around. In the quantum world, it's tied to motion and gravity's grip on spacetime itself. Picture a distant observer watching someone fall toward a black hole. From afar, the falling astronaut seems to freeze at the horizon, their light redshifting into oblivion. But from the astronaut's perspective, they plunge through effortlessly. This mismatch in perspectives, what physicists call complementarity, creates the Hawking glow. Virtual particle pairs flickering at the horizon get split, one falling in while the other escapes as real radiation. The black hole isn't radiating because it's hot in the conventional sense. It's radiating because the vacuum structure near the horizon distorts reality into a thermal mirage. The Unruh effect mirrors this in motion. Imagine strapping into a rocket accelerating at 1 trillion times Earth's gravity. Outside, space looks empty. But to you, the vacuum teems with particles at a temperature proportional to your acceleration, like cosmic friction, heating the void around you. This isn't just theory. While we can't yet accelerate objects fast enough to measure Unruh radiation directly, analog experiments with superfluid helium and Bose-Einstein condensates have observed similar thermal effects tied to motion, lending credence to the idea that the vacuum responds dynamically to acceleration. The kicker: these temperatures aren't mere bookkeeping. Hawking radiation implies black holes slowly lose mass, evaporating over eons. Unruh radiation suggests that even in empty space, relentless acceleration could cook you from the outside in. And both hint that thermodynamics isn't just about atoms bouncing around, it's woven into spacetime's fabric. The vacuum's temperature isn't an illusion, it's a window into how deeply heat, motion, and gravity are entangled at the quantum level. Absolute zero might be unreachable not because of engineering limits, but because the universe refuses to let even nothingness stay truly cold. Yet the most haunting implication lies in the vacuum's silence. These thermal effects are minuscule under everyday conditions. A black hole the mass of our sun would glow at 60 billionths of a degree above absolute zero. But their existence forces us to ask, is the vacuum's temperature a local effect, or does empty space itself have a baseline warmth? Some models suggest that dark energy could be linked to a universal vacuum temperature, a faint heat left over from inflation or woven into spacetime's expansion. Others speculate that in the far future, as the universe cools toward absolute zero, these quantum thermal effects might become the only heat left, a final, flickering candle in an otherwise frozen cosmos. One thing's certain, the vacuum's temperature shatters the old idea that heat requires matter to carry it. Instead, it reveals a universe where emptiness itself can burn or freeze depending on how you move through it, where black holes shimmer with quantum warmth, and where the simple act of accelerating can turn the void into a furnace. The coldest places in existence might not be cold at all, just waiting for the right observer to reveal their hidden fire. In the quantum vacuum, even something as fundamental as electric charge isn't quite what it seems. Picture an electron floating in empty space. Classically, we'd imagine it as a tiny, solitary point of negative charge, simple and unchanging, but the vacuum has other plans. At any moment, a storm of virtual particles erupts around it, electron-positron pairs flickering in and out of existence like fireflies in a midnight breeze. These fleeting particles don't just vanish without a trace, they leave behind an invisible fingerprint, subtly reshaping how the electron's charge interacts with the world. This is vacuum polarization, a phenomenon so pervasive that without it, our entire understanding of particle physics would crumble. Here's how it works. When a virtual positron, the electron's antimatter twin, is momentarily pulled toward the real electron, while the virtual electron is repelled, the vacuum acts like a cosmic funhouse mirror. The electron's negative charge becomes partially screened by this dance, as if wrapped in a fog of shifting polarity. From far away, its charge appears weaker than it truly is at close range. It's not magic, it's the vacuum playing puppeteer with the very forces that hold atoms together. This effect isn't just theoretical sleight of hand. It's been measured with jaw-dropping precision in hydrogen atoms, where vacuum polarization tweaks the energy levels of electrons by a hair's breadth. Without accounting for this, quantum electrodynamics predictions would be off by a factor of 1,000. But when physicists fold in the vacuum's polarizing influence, theory and experiment align to within 1 part in a billion, the most accurate match in all of science. Yet the implications run deeper than atomic fine-tuning. Vacuum polarization forces physicists to confront one of quantum field theory's most notorious headaches, infinities. When calculating interactions between particles, the math often spirals into nonsensical infinite values until renormalization steps in. This mathematical cleaning process subtracts the infinite contributions of virtual particles, leaving behind finite, measurable quantities like charge and mass. It's as if the vacuum's wild fluctuations create a cacophony of noise, and renormalization is the filter that lets the true signal shine through. Critics once called it a fudge, but today it's recognized as the universe's way of hiding its messy quantum plumbing behind a curtain of observable simplicity. The real shocker, vacuum polarization isn't static. In extreme environments like near a supercharged atomic nucleus or inside a neutron star, the screening effect intensifies. An electron racing through these warped spaces experiences a charge landscape that shifts like sand beneath its feet. Some theories even suggest that in the searing heat of the early universe, vacuum polarization might have briefly altered the strength of electromagnetism itself, leaving echoes in the primordial light we now see as the cosmic microwave background. So the next time you think of an electron, don't picture a lonely dot of charge. Imagine it instead as a flickering nexus, shrouded in a quantum fog, a particle and its ghostly entourage forever dancing to the vacuum's invisible tune. What we measure as fundamental constants might just be the universe's way of averaging out this endless subatomic masquerade. In the early days of quantum mechanics, physicist Paul Dirac stumbled upon an equation that seemed too strange to be true. One that described electrons so perfectly it accidentally revealed a hidden universe beneath our own. His math insisted that for every possible state an electron could occupy, there had to be a mirror image, a shadow world of infinite, invisible electrons filling what became known as the Dirac sea. This wasn't just abstract theory. Dirac's sea of negative energy predicted the existence of antimatter years before the positron was discovered, turning science fiction into laboratory fact. At first glance, the idea sounds surreal. Imagine the vacuum as an ocean, its depths packed with electrons so tightly they form an invisible, uniform background. Normally, we'd never notice this sea. It's like trying to hear a single note in a symphony playing at full volume. But when enough energy punches through, an electron can be kicked out of this submerged crowd, leaving behind a hole that behaves exactly like a particle with opposite charge, antimatter. Dirac's hole theory was the first hint that empty space might be a crowded quantum metropolis, teeming with particles we simply couldn't see. The discovery of the positron in 1932 stunned the physics world. Cosmic rays striking Earth's atmosphere revealed tracks that curved the wrong way in magnetic fields, particles identical to electrons but with positive charge. Suddenly, Dirac's sea wasn't just a mathematical quirk, it was a roadmap to a hidden layer of reality. Yet as quantum field theory evolved, physicists realized they didn't need an infinite ocean to explain antimatter. Instead, they reinterpreted the Dirac sea as a vivid metaphor for quantum fields constantly oscillating between positive and negative energy states. Modern physics paints an even weirder picture. The vacuum isn't a static sea but a froth of quantum fields where particles and antiparticles blink into existence like sparks from a cosmic fire. Dirac's negative energy states. They're now seen as antiparticles traveling backward in time, a concept baked into Feynman diagrams, those squiggly lines physicists used to map particle interactions. It's as if the universe keeps its books balanced by allowing temporary withdrawals from the energy bank, so long as every debt gets repaid. But the Dirac sea hasn't completely faded into history. In condensed matter physics, materials like graphene and topological insulators behave as if their electrons are swimming in a Dirac sea, offering lab-scale models of relativistic quantum effects. Some theories even suggest that dark matter or other exotic particles might still lurk in a modern reinterpretation of Dirac's original vision. The most profound legacy, though, is how Dirac's equation revealed the universe's love of symmetry. For every particle, an antiparticle, for every up, a down. The vacuum might not be an infinite sea of electrons anymore, but it's still a place where opposites dance on the edge of reality, and where the boldest equations can predict discoveries before we've even built the tools to find them. What if the quantum vacuum isn't just a chaotic sea of particles, but a labyrinth of hidden tunnels, cosmic shortcuts stitching the fabric of spacetime itself? This is the wild frontier where topology, the study of shapes and connections, collides with quantum gravity, suggesting that the vacuum's geometry might be far stranger than we ever imagined. Picture spacetime not as a flat, rigid grid, but as a malleable fabric full of folds, twists, and perhaps even wormholes, hypothetical bridges linking distant points in the universe like a cosmic subway system. The seed of this idea comes from an astonishing proposal called ER equals EPR, a conjecture forged by physicists Juan Maldacena and Leonard Susskind. At first glance, it looks like alphabet soup, but the implications are profound. It suggests that entangled particles, those spookily connected quantum partners, might be tied together by microscopic wormholes threading through the vacuum. In other words, Einstein-Rosen bridges, the ER in the equation, could be the physical manifestation of quantum entanglement, the EPR. It's as if the vacuum isn't just empty space, but a vast, intricate network of invisible tunnels, with every entangled pair holding open a tiny door between them. Visualize it this way. Take two pieces of paper representing distant points in space. Normally, the shortest path between them is a straight line. But if you fold the papers so the points touch, suddenly the distance collapses. That's the essence of a wormhole, a topological trick where the vacuum structure allows spacetime to pinch and reconnect. And if the ER equals EPR idea holds, then every time particles become entangled, the vacuum might be secretly knitting these tunnels into existence, weaving the universe together at a level deeper than we can see. The math behind this is both elegant and mind-bending. In theoretical models like the AD-S/CFT correspondence, a framework linking quantum physics to higher-dimensional gravity wormholes emerge naturally as geometric representations of quantum entanglement. The vacuum's fluctuating fields don't just spawn particles, they might also sculpt spacetime's very geometry, creating transient wormholes that vanish as quickly as they form. Some researchers even speculate that black holes, those ultimate spacetime warpers, could be connected by wormholes with their interiors leading to other universes or distant corners of our own. But here's the catch: these wormholes, if they exist, aren't the Stargate-style passages sci-fi loves. They'd be vanishingly small, unstable, and might only persist for fractions of a second before the vacuum's energy snaps them shut. Traversing one would require exotic matter with negative energy to prop it open, something we've never observed naturally. Yet the mere possibility reshapes how we think about the vacuum's role in reality. Instead of a passive backdrop, it becomes an active architect, folding spacetime into shapes that defy classical intuition. The implications ripple outward. If wormholes are entangled particle pairs in disguise, could we manipulate entanglement to engineer spacetime tunnels? Quantum gravity theorists are already exploring this, sketching blueprints for how quantum computers might one day simulate wormhole dynamics. And if the vacuum's topology is this malleable, it might finally bridge the gap between quantum mechanics and general relativity, the holy grail of modern physics. Of course, skeptics wave caution flags. Wormholes remain firmly in the realm of theory, and the energy scales involved are far beyond anything we can probe experimentally. Yet the mathematics refuses to dismiss them. From the holographic principle to string theory, the idea that the vacuum's hidden geometry could enable spacetime shortcuts keeps resurfacing, a ghostly hint that our universe's wiring might be more interconnected than we ever dreamed. So the next time you hear about quantum entanglement, don't just think of spooky action at a distance. Imagine the vacuum as a master weaver, threading unseen tunnels through the cosmic fabric, each entangled pair a stitch in spacetime's secret blueprint. The universe's emptiest spaces might be its busiest construction sites, and if we're lucky, one day we'll catch it in the act. One of the greatest embarrassments in modern physics hides in plain sight, a problem so glaring it's called the vacuum catastrophe. Here's the heartbreak: when we calculate how much energy the quantum vacuum should contain based on particle physics, the numbers explode to infinity. Yet when we measure the vacuum's actual gravitational effect, how it bends spacetime, the energy is almost zero. The mismatch isn't just a rounding error, it's a factor of 10 to the power of 120. That's a 1 followed by 120 zeros, the worst wrong prediction in the history of science. Digging deeper, the crisis stems from two clashing visions of reality. Quantum field theory treats the vacuum as a seething foam of virtual particles, each contributing boundless energy. Yet general relativity insists that all energy, including the vacuums, must curve spacetime. If our quantum math were right, the universe's expansion should have torn apart atoms before stars ever formed. Instead, cosmic surveys show the vacuum's gravity is absurdly tiny, barely nudging galaxies apart. It's as if nature installed a cosmic dimmer switch, turning the vacuum's energy down to a faint whisper. String theory offers one escape route. In this framework, the vacuum isn't just a chaotic particle soup, but a finely tuned symphony of vibrating strings. The extra dimension string theory predicts tiny, curled-up shapes at every point in space might cancel out most of the vacuum's energy through perfect symmetry. Picture a high-wire walker balancing with a pole. The infinite energies from virtual particles could be counterweighted by opposing forces in hidden dimensions, leaving only the faint residue we detect as dark energy. Loop quantum gravity, string theory's rival, takes a different approach. It suggests spacetime isn't smooth and continuous but woven from discrete, indivisible loops like pixels on a cosmic screen. At these microscopic scales, the vacuum's energy might hit a natural ceiling, preventing the infinity problem altogether. Think of it like a digital photo. Zoom in too far, and you hit individual pixels rather than an endless blur. The vacuum catastrophe could simply vanish when physics acknowledges spacetime's granular structure. Yet the most radical solution comes from an idea called supersymmetry. It proposes that every known particle has an undiscovered superpartner, a heavier twin that cancels out its quantum quirks. In a supersymmetric universe, positive and negative vacuum contributions would balance perfectly, leaving near zero net energy. The catch: we've hunted for these superparticles for decades with no luck. If they exist, they're far heavier than predicted, meaning nature's ledger still doesn't quite add up. The vacuum catastrophe isn't just academic, it's a flashing red light that our deepest theories are incomplete. Whether the answer lies in extra dimensions, quantum knots, or undiscovered particles, one thing's certain: the void has more to teach us. Until then, this staggering mismatch stands as both an indictment of our ignorance and an invitation to look deeper. The vacuum's silence might be the loudest clue we've ever been handed. Ever tried turning nothing into something just by moving your hands? That's essentially what physicists pulled off with the dynamical Casimir effect, a bizarre quantum trick where mirrors shaken fast enough in a vacuum create real light from pure emptiness. It sounds like alchemy, but it's one of the most jaw-dropping validations of quantum field theory ever caught in a lab. Here's the sorcery at work. Remember the standard Casimir effect, where two motionless plates in a vacuum get pushed together by quantum fluctuations. Now imagine one of those plates suddenly lurching at nearly the speed of light. The abrupt motion distorts the vacuum's quantum field so violently that virtual photons, normally fleeting ripples in the void, get kicked into reality, becoming measurable light. It's like snapping a towel so fast that the whip-crack sound isn't just noise, it's an actual object materializing in midair. The experiment that proved this was a masterpiece of precision. In 2011, physicists in Sweden used a superconducting quantum interference device, or SQUID, to mimic a mirror vibrating at a quarter of light speed. By modulating magnetic fields, they made the SQUID surface oscillate faster than a hummingbird's wings, shredding the vacuum's delicate balance. The result: microwave photons popping into existence exactly as predicted, twins emerging from the quantum foam with matching frequencies. A smoking gun for real particles born from motion alone. Why does this matter? For starters, it reveals how deeply motion and acceleration are tied to the vacuum's structure. The universe isn't just a static stage, it's a responsive medium where even mirrors can become photon factories if you move them right. This effect also blurs the line between classical motion and quantum creation, suggesting that extreme acceleration, like near black holes or in particle colliders, might unravel spacetime's fabric in ways we're only beginning to grasp. But the wildest implications lie in quantum technology. The dynamical Casimir effect isn't just a curiosity, it's a blueprint for generating entangled photons on demand, a holy grail for quantum computing and secure communication. Those photon pairs spawned by the shaking mirror, they're perfectly linked, sharing quantum states instantly across any distance. Harness this, and we could build light sources that fabricate entanglement like a 3D printer spools out plastic, revolutionizing how we process information. Yet the phenomenon also whispers of deeper mysteries. If motion through the vacuum can conjure light, what else might acceleration unlock? Some theories suggest similar mechanisms could explain UNRA radiation or even dark energy's repulsive force. Others wonder if the early universe's violent expansion acted like a cosmic Casimir mirror, flooding space with primordial photons that still echo as the cosmic microwave background. The takeaway: the vacuum isn't just empty space, it's a reservoir of untapped potential, waiting for the right nudge to spill its secrets. And with each experiment, we're learning that the universe's most powerful tricks don't require magic wands or star cores. Sometimes all it takes is a mirror moving fast enough to shake reality itself. Light doesn't just travel through empty space, it dances with it. And nowhere is this cosmic ballet more striking than near neutron stars, where magnetic fields so powerful they could strip atoms apart force the vacuum itself to bend light in bizarre new ways. This is vacuum birefringence, a phenomenon where the quantum vacuum becomes an optical lens under extreme conditions, splitting light like a prism made of pure nothingness. Picture a neutron star, a city-sized remnant of a supernova, spinning faster than a blender and wielding magnetic fields a trillion times stronger than Earth. In this environment, the vacuum isn't passive. Its virtual particles align like microscopic compass needles along the magnetic field lines, creating a sort of quantum hall of mirrors. When light passes through this polarized void, it doesn't travel uniformly. Instead, it separates into two distinct beams, each vibrating at right angles to the other, like headlights refracting through a diamond. One beam slows slightly, while the other races ahead, an effect called birefringence, normally seen in crystals but here emerging from the structure of space itself. The first smoking gun for this came from the European Space Agency's XMM Newton telescope, studying a neutron star 400 light-years away. As X-rays streamed from its surface, their polarization, the direction their waves vibrated, shifted in a way that matched precisely what quantum electrodynamics predicts for vacuum birefringence. It's as if the vacuum near the star had morphed into a colossal optical filter, twisting light's path just by the sheer force of its magnetic grip. But why does this matter beyond cosmic curiosities? Because it reveals a fundamental truth: the vacuum isn't just there, it interacts. Like water bending a straw in a glass, the quantum void reshapes reality under the right conditions. If electromagnetic fields can polarize the vacuum this dramatically, what else might warp it? Some theories suggest gravitational waves could induce similar effects, subtly coloring starlight as it traverses warped spacetime. Others speculate that vacuum birefringence might leave faint echoes in the cosmic microwave background, a fossilized imprint from the universe's first magnetic fields. Neutron stars aren't the only laboratories. Powerful lasers like those at the Eli facility in Europe are now attempting to recreate this effect on Earth by firing beams so intense they briefly mimic neutron star conditions. While we can't yet bend light with pure magnetism in a lab, each experiment inches us closer to proving that even in a vacuum, there's no such thing as nothing. Space isn't just the absence of matter. It's an active participant, flexing, refracting, and reshaping light itself when pushed to extremes. The real magic lies in what this means for our cosmic toolkit. By studying how light twists near these stars, astronomers could map neutron star magnetic fields more precisely than ever, unlocking secrets about how matter behaves under pressures that crush atoms into quantum soup. It might even help explain fast radio bursts, those enigmatic cosmic sirens whose polarized signals could be vacuum birefringence fingerprints. So the next time you look up at the night sky, remember, even in the darkest void between stars, the universe is playing tricks with light. The vacuum isn't empty, it's a chameleon, changing its stripes under the influence of forces so immense they turn nothingness into a lens. And in that bending, that subtle splitting of beams, we're glimpsing a hidden layer of reality where space itself is an optical illusion waiting to be decoded. What if everything you see around you, the stars, your hands, even the air you breathe, is just a projection, like a movie screen casting shadows that trick us into thinking they're real? This isn't science fiction. It's the holographic principle, one of the most radical ideas in modern physics. And the quantum vacuum might be the canvas where this cosmic illusion is painted. At its heart lies a staggering claim: Our three-dimensional universe, with all its depth and complexity, could be encoded on a two-dimensional surface at its edges, like a hologram storing a 3D image in flat layers of light. The roots of this idea stretch back to black holes, those cosmic shredders where gravity is so strong even light can't escape. In the 1970s, physicist Jacob Bekenstein calculated that a black hole's entropy, a measure of its hidden information, isn't scattered throughout its volume but plastered across its event horizon, the point of no return. Each square Planck length, that's 10 to the minus 35 meters of the horizon, holds exactly one bit of information, as if the black hole's entire interior were a data storage unit with its contents printed on the surface. This discovery hinted at something profound. The vacuum surrounding a black hole might not be empty but a buzzing hard drive, encoding reality in pixels far smaller than atoms. Fast forward to 1997, when physicist Juan Maldacena turned this hint into a full-blown revolution. His AD/CFT correspondence, a mouthful standing for anti-de Sitter/conformal field theory, proposed a precise mathematical duality between a higher-dimensional universe with gravity, the bulk, and a lower-dimensional world without it, the boundary. Picture a soup can where the label holds all the information needed to reconstruct the soup inside. In Maldacena's model, the quantum vacuum isn't passive, it's a dynamic boundary where fields and particles are shadows of deeper holographic processes. Here's where it gets spine-tingling. If the holographic principle holds, then the vacuum fluctuations we've been exploring, virtual particles, zero-point energy, even entanglement, might just be glitches in the projection. Take two entangled particles. From our 3D perspective, they're mysteriously linked across space. But on the 2D boundary, they could be single points connected by simpler, non-local rules like dots on a map joined by straight lines. The vacuum's infinite complexity would then be an illusion, a cosmic sleight of hand where depth emerges from flatness. Black holes test this idea brutally. When matter falls into one, classical physics says its information is lost forever, violating quantum mechanics' sacred rule that information can't be destroyed. But if the holographic principle is right, that information isn't gone. It's smeared across the event horizon, preserved in scrambled form like a burned book whose ashes still hold every word if you know how to read them. The vacuum around a black hole becomes a frenetic encoder, translating 3D chaos into 2D order, ensuring no data is ever truly erased. Experiments are catching up. In 2017, physicists used quantum computers to simulate holographic universes, confirming that information on a lower dimensional boundary could indeed generate higher dimensional physics. And gravitational wave detectors might one day spot subtle holographic noise in spacetime's fabric, ripples betraying the pixelated grid beneath our smooth reality. Yet the biggest question lingers: if we're living in a hologram, what's projecting it? Some theories suggest the vacuum itself is the projector, its quantum fields acting like pixels on a universal screen. Others speculate that our entire cosmos could be the interior of a black hole in some higher dimensional space, its event horizon holding the true laws of reality while we're trapped inside the simulation. Whether metaphor or literal truth, the holographic principle forces us to confront a dizzying possibility: that the quantum vacuum isn't just the stage for reality but the script, the director, and the screen all at once. Every particle, every force, even time itself might be subtitles in a language written on the edge of the universe, waiting for us to decode them. And if that's true, then the greatest magic trick of all isn't pulling rabbits from hats, it's convincing us that emptiness is anything but empty. Imagine a universe where nothing has weight, where electrons zip around at light speed, atoms can't form, and stars never ignite. That could have been our reality if not for a cosmic game of hide and seek playing out in the quantum vacuum. The secret lies in symmetry breaking, a phenomenon where the pristine order of the early universe cracked, gifting particles with mass and sculpting the physics we know today. At the heart of this transformation, the Higgs field, an invisible ocean filling every inch of space, its interactions with other particles turning the vacuum into a sort of cosmic molasses that slows some while letting others glide freely. Rewind to the universe's first trillionth of a second. Back then, electromagnetism and the weak nuclear force weren't separate phenomena but unified as a single electroweak force, much like ice and steam are just different states of water. Particles like electrons and quarks moved at light speed, massless and unburdened. But as the cosmos cooled, the vacuum underwent a phase transition. Think of it like water freezing into ice, except instead of crystals forming, the Higgs field shifted from a high-energy state to a lower, stable one. This shift broke the electroweak symmetry, splitting it into the distinct forces we recognize today, and giving some particles resistance as they moved through the newly treacly vacuum. The Higgs mechanism works like this. Particles that interact strongly with the Higgs field, like quarks and electrons, experience more drag, acquiring what we perceive as mass. Others, like photons, glide through untouched, remaining massless. It's as if the vacuum became a crowded room. Some particles elbow their way through slowly, while others slip past unnoticed. The Higgs boson, discovered in 2012 at CERN, is the ripple in this field, the tangible proof of the vacuum's hidden structure, yet mysteries linger. Why do particles have the masses they do? The Higgs field assigns mass, but the values seem arbitrary. An electron is about 200,000 times lighter than a top quark, yet both get their mass from the same vacuum interaction. Some theories suggest undiscovered particles or additional Higgs fields might fine-tune these numbers, while others propose wilder ideas, like mass being a projection from extra dimensions. And then there's the vacuum's stability. If the Higgs field's current state isn't the lowest possible energy level, another catastrophic symmetry breaking could lie in our future, rewriting physics in an instant. The beauty of symmetry breaking is how it turns uniformity into diversity. What began as a featureless, symmetric cosmos became a world rich with structure, atoms, chemistry, life itself, all because the vacuum chose one configuration over another. It's a reminder that emptiness isn't passive. It's the silent architect of reality, hiding its most transformative acts behind the curtain of nothingness. And somewhere in those hidden folds, the next great cosmic revelation might be waiting for us to stumble upon it. You'd think the laws of thermodynamics are set in stone. Energy can't be created or destroyed. Entropy always increases, and extracting work from a system has hard limits. But the quantum vacuum laughs at these rules. In the bizarre realm of non-equilibrium thermodynamics, a principle called the Jarzynski equality reveals how vacuum fluctuations can be harnessed to bend or even break classical energy constraints. It's as if the universe keeps a secret ledger, allowing temporary withdrawals from its energy reserves so long as the books balance in the end. Picture this: a microscopic engine smaller than a virus, its pistons buffeted by the vacuum's relentless particle-antiparticle fireworks. Classically, the work you could extract from such a chaotic system would be capped by the second law of thermodynamics. But in the quantum world, something extraordinary happens. The Jarzynski equality proves that even when a system is violently yanked out of equilibrium like a piston jerked at lightning speed, the average work extracted can defy classical limits thanks to the vacuum's chaotic energy loans. It's not magic, it's math. The equation ties together the statistical fluctuations of a system's energy with the free energy difference between its initial and final states, revealing that rare, extreme event, like a vacuum fluctuation gifting you an energy windfall, can skew the average in ways that seem impossible. Lab experiments with trapped ions and Brownian particles have confirmed this effect. By rapidly changing parameters like magnetic fields or laser pressures, researchers observed particles briefly cheating the energy conservation rule, gaining bursts of work that classical physics wouldn't allow. These aren't measurement errors, they're glimpses of the vacuum's ledger at work, where temporary imbalances are later repaid by equally rare energy deficits. The kicker: over many trials, everything averages out to satisfy thermodynamics, but in any single experiment, the universe might hand you a free lunch. This isn't just theoretical sleight of hand. The implications ripple into nanotechnology and quantum computing. Imagine engineered enzymes that exploit vacuum fluctuations to perform mechanical work, or molecular motors that operate beyond Carnot efficiency limits. Even error correction in quantum computers could benefit, as Jarzynski-inspired protocols might recover energy dissipated during qubit operations. The vacuum's chaos isn't just noise, it's a resource waiting to be tapped. Yet the deepest lesson lies in what this says about reality. The Jarzynski equality bridges the microscopic frenzy of quantum fluctuations with the macroscopic certainty of thermodynamics, proving that the second law isn't an iron rule but a statistical tendency. The vacuum's randomness doesn't just fill empty space, it rewrites the rules of work, energy, and maybe even time itself. And somewhere in those fleeting fluctuations, the universe might be hiding its next great loophole. Deep in the quantum vacuum, hidden beneath the chaos of virtual particles and fluctuating fields, might lie the answer to one of cosmology's greatest puzzles: dark matter. This invisible substance, which outweighs ordinary matter 5 to 1, has eluded detection for decades. But what if we've been searching in the wrong places? Instead of exotic particles from distant galaxies, dark matter could be lurking right under our noses, woven into the fabric of empty space itself. Enter action's hypothetical particles so lightweight and shy they barely interact with anything, making them perfect dark matter candidates. Theorized in the 1970s to solve a puzzle in quantum chromodynamics, these ghostly particles could arise naturally from vacuum condensates, regions where quantum fields settle into low-energy configurations, like droplets forming on a cold surface. Picture the vacuum as a vast ocean of energy, and actions as ripples moving through it, too subtle to see but collectively massive enough to shape galaxies with their gravity. Unlike weakly interacting massive particles, which have dominated dark matter hunts for years, actions wouldn't require new physics beyond the standard model, just a deeper understanding of how the vacuum organizes itself when left undisturbed. The math is tantalizing. In certain high-energy theories, the vacuum structure could produce actions in staggering numbers during the early universe, like a cosmic ice age freezing primordial energy into invisible crystals. These particles would be absurdly light, perhaps a trillionth the mass of an electron, but so abundant that their combined gravitational pull could explain why galaxies rotate faster than visible matter alone predicts. Even stranger, actions might behave more like waves than particles, their quantum coherence stretching across light years, creating interference patterns that subtly tweak the behavior of stars and gas clouds. Experiments are closing in. Devices like the Action Dark Matter experiment (ADMX) use powerful magnets to convert actions into detectable microwave photons, essentially turning the vacuum's hidden vibrations into a signal we can measure. Meanwhile, astrophysical clues like unexplained X-ray emissions from neutron stars hint that actions might occasionally decay into photons when bathed in intense magnetic fields. These observations are still controversial, but they point to a thrilling possibility: that dark matter isn't some distant anomaly but a fundamental feature of the vacuum's architecture. Yet actions aren't the only vacuum-born dark matter suspects. Some theories propose other ultralight particles, like hidden photons or sterile neutrinos, emerging from vacuum phase transitions, abrupt shifts in the quantum field state, like water boiling into steam. These particles could form mysterious, fuzzy, dark matter, with wave-like properties that prevent them from clumping like traditional matter, explaining why galaxies lack the dense central cusps predicted by older models. The stakes couldn't be higher. If dark matter is indeed a vacuum phenomenon, it would mean that the universe's largest structures, galaxy clusters, cosmic webs, are sculpted by the quietest, most pervasive aspect of reality. The same void we once called nothing might be the unseen hand guiding everything. And if we're right, the key to unlocking this mystery won't be found in a distant supercollider or a telescope pointed at the stars, but in the quantum whispers of empty space itself waiting for us to finally listen. One of the most surreal light shows in nature happens not in the depths of space, but in a glass of water. It's called sonoluminescence, a phenomenon where sound waves violently collapse microscopic bubbles, creating flashes of light so intense they rival the surface of the sun. And here's the twist: this bizarre spectacle might be a direct window into the quantum vacuum's hidden energy, twisting empty space itself into a cosmic light bulb. Picture a tiny air bubble suspended in liquid no wider than a human hair. When bombarded with ultrasonic sound waves, the bubble contracts faster than the speed of sound, compressing its contents to temperatures hotter than the sun's core. At the moment of collapse, something impossible happens. A pulse of blue or ultraviolet light bursts forth, lasting just trillionths of a second but packing enough energy to strip electrons from atoms. For decades, this seemed like a thermodynamic curiosity until physicists realized the numbers didn't add up. The heat alone couldn't explain the light's intensity. The secret: the vacuum itself might be amplifying the effect, turning a simple bubble into a quantum pressure cooker. Here's how the pieces fit. As the bubble implodes, its walls accelerate so rapidly that they distort the surrounding quantum vacuum, squeezing virtual particles into reality. Some theories suggest that the extreme pressures create Casimir-like effects inside the bubble, where the vacuum's fluctuations are pinched so tightly that they release energy as light. Others propose that the bubble's collapse briefly forms a plasma so dense it interacts directly with the vacuum's zero-point energy, like striking a match against the fabric of spacetime. Either way, the result is the same. The void itself becomes a participant, converting sound into light through mechanisms we're still unraveling. Lab experiments have pushed this phenomenon to even wilder extremes. By doping water with noble gases like xenon or krypton, researchers have produced sonoluminescence flashes bright enough to capture Chinese letter cameras, their spectra revealing temperatures exceeding 20,000 Kelvin. That's hotter than the surface of most stars, all from a bubble vanishing in a fraction of a microsecond. Even stranger, the light sometimes pulses with clockwork regularity, as if the vacuum is resonating at a frequency beyond our current math. The implications ripple far beyond a lab party trick. If sonoluminescence taps into vacuum energy, it could reshape our understanding of energy transduction, how one form of energy morphs into another. Some engineers dream of vacuum batteries, where controlled bubble collapses harvest zero-point energy, though the hurdles are astronomical. More immediately, studying these flashes might help us simulate extreme astrophysical environments, like the crushing pressures inside neutron stars or the chaotic plasma of the early universe. Yet the deepest mystery remains unsolved. Is the light purely a classical effect, or does it truly reveal the vacuum's hand? Future experiments with even finer control over bubble dynamics, perhaps using quantum dots or artificial microcavities, could tease apart the answer. Until then, sonoluminescence stands as a shimmering enigma, a reminder that even in the most ordinary settings, the universe hides pockets of brilliance where sound, light, and the quantum void dance on the edge of the impossible. And in that fleeting glow, we might just catch a glimpse of the vacuum's true power, not as empty space, but as a forge where energy and matter trade shapes in the dark. Gravity doesn't play by the same rules as the other forces, and the quantum vacuum might hold the key to why. While electromagnetism, the strong nuclear force, and even the weak force all bow to the precise equations of quantum field theory, gravity stubbornly resists quantization, as if the vacuum itself refuses to let spacetime be chopped into neat little packets. This cosmic standoff isn't just a technical hiccup, it's a clash between two visions of reality, with the vacuum as the battleground, take the graviton, the hypothetical particle that should mediate gravity in quantum terms. Photons carry electromagnetic forces, gluons bind quarks, but gravitons, they're ghosts predicted by theory yet impossible to detect, assuming they even exist. The problem isn't just their weakness, it's that gravity isn't a force in the traditional sense. Unlike other interactions which happen within spacetime, gravity is spacetime, the curvature of the cosmic stage itself. Trying to quantize gravity is like trying to pixelate a theater's floor while the play is ongoing. The vacuum structure doesn't just host gravity, it's interwoven with it, making every attempt to isolate gravitons akin to plucking a single thread from a tapestry and expecting the whole picture to stay intact. Now zoom into the Planck scale, where spacetime itself might dissolve into a seething foam of virtual black holes and wormholes, a concept dreamed up by John Wheeler in the 1950s. Here, the vacuum isn't smooth and continuous but a chaotic froth, with bubbles of distorted geometry popping in and out of existence. In this realm, gravitons could emerge and vanish before they ever stabilize, drowned out by the noise of spacetime's quantum turbulence. It's as if the vacuum treats gravity like an outlaw, its effects too deeply baked into existence to be neatly packaged like other forces. String theory offers a potential escape route, suggesting gravitons could be vibrating strings in higher dimensional space, but even there, the vacuum's role gets murky. Extra dimensions might dilute gravity's strength, explaining why it's so weak compared to other forces. Yet after decades of searching, no experimental evidence supports these ideas, leaving the vacuum's relationship with gravity as one of physics' most tantalizing dead ends. Meanwhile, loop quantum gravity takes a radically different approach, proposing that spacetime is woven from indivisible loops, tiny, intersecting threads of vacuum energy. In this view, gravitons aren't particles but twists in the fabric, knots of spacetime's underlying structure. It's a compelling image, but one that still can't reconcile why gravity alone refuses to quantum cooperate. The deeper we dig, the clearer it becomes. The vacuum isn't just empty space. It's the mediator, the rulebook, and the referee in gravity's quantum rebellion. Until we crack its code, the universe's most familiar force will remain its most enigmatic. Imagine a computer so powerful it could solve problems in seconds that would take classical machines billions of years. A machine where the calculations don't happen inside silicon chips, but in the seething quantum foam of empty space itself. This isn't science fiction. Cutting-edge theories suggest the vacuum might not just host quantum computations. It could be the ultimate computer, with every fluctuation a logic gate and every virtual particle a bit of data in the universe's most alien processing system. At the heart of this idea lies a radical reimagining of what computation even means. Traditional computers rely on binary states, zeros and ones etched into transistors. Quantum computers upgrade this with qubits that can be 0, 1, or both simultaneously thanks to superposition. But the vacuum's computational framework could dwarf both. Think of virtual particles as transient qubits popping into existence already entangled, performing calculations through their interactions, then vanishing before decoherence can corrupt the results. It's like a cosmic version of scratch paper, the universe scribbling down intermediate answers in the margins of reality before erasing them. Some models propose that vacuum fluctuations could execute instantaneous computations by exploiting non-local entanglement, solving optimization problems across vast distances without signal delays. The implications for speed are staggering. In 2018, physicists demonstrated how quantum fields in a vacuum could theoretically solve the traveling salesman problem, a notoriously complex puzzle, by encoding all possible routes simultaneously in the vacuum superposition of states. Unlike classical or even standard quantum computing, which require exponential time for certain tasks, the vacuum's natural parallel processing might crack them in polynomial time, as if the universe had been running hyper-efficient algorithms in the background all along. Even wilder is the notion that the vacuum could host consciousness. Or theory, championed by physicist Sir Roger Penrose, suggests quantum processes in microtubules within brain cells might enable consciousness by tapping into spacetime's fundamental geometry. Extend this idea, and the vacuum, with its ceaseless quantum activity and entanglement networks, could form a substrate for cosmic-scale awareness. It sounds like metaphysics, but mathematically, there's an eerie resonance here. If the vacuum's fluctuations can store and process information, could they also generate self-referential loops complex enough to experience? Some theorists speculate that advanced civilizations might even upload themselves into such a substrate, becoming patterns in the quantum foam itself. Of course, obstacles loom. Decoherence, the bane of quantum computing, would plague vacuum-based systems too, unless some as yet unknown physics stabilizes them. And extracting usable data from the vacuum's chaos would require technologies we can barely conceive of, like quantum plungers, to siphon coherent answers from the noise. Yet lab experiments with Casimir cavities and optical lattices are already probing how vacuum states can be manipulated for information storage, hinting that nature might have been ahead of us all along. Whether the vacuum is truly computing or not, one thing's certain: its fluctuations aren't just random static. They're a dynamic, interconnected web, a language the universe might be using to solve problems we're only beginning to frame. And if we ever learn to speak that language, the answers we find could rewrite not just technology, but our understanding of reality itself. Time flows like a river, always forward, never backward. Drop milk into coffee and it mixes effortlessly, but no matter how long you wait, it never unmixes itself. This relentless one-way march is called the arrow of time, and for centuries, physicists have wrestled with why the universe enforces such strict asymmetry. Surprisingly, the answer might be hiding in the quantum vacuum's hidden chaos, not in stars or particles, but in the restless fluctuations of empty space itself. At first glance, quantum mechanics treats time as reversible. The equations governing electrons and photons work just as well whether time runs forward or backward. Yet we never see broken eggs reassemble or smoke funneling back into a cigarette. The disconnect lies in something called decoherence, the process where quantum systems lose their delicate superpositions and collapse into definite states. And here's where the vacuum enters the picture. Its ceaseless activity might be the invisible hand that nudges reality irreversibly toward disorder. Think of a flipped coin mid-spin, a perfect superposition of heads and tails. In an isolated world, it could hover in that fuzzy state forever, but the vacuum doesn't allow isolation. Virtual particles bombard the coin, their random interactions collapsing the superposition like gusts of wind deciding which way the coin falls. Each collision transfers information about the coin's state into the vacuum's inaccessible depths, a microscopic betrayal of reversibility. Multiply this effect across every quantum interaction in the universe, and you get an avalanche of decoherence, a relentless push toward states where time's arrow points decisively forward. Entropy, the measure of disorder famously described by the second law of thermodynamics, might be the macroscopic echo of this quantum unraveling. When milk disperses in coffee, its molecules explore countless configurations, but the vacuum's decoherence ensures they never spontaneously return to their original arrangement. The vacuum acts like a cosmic scribe, constantly recording choices in a ledger that can't be erased. Some theorists argue that without this vacuum-induced decoherence, time's arrow might wobble or even reverse in isolated quantum systems, though no experiment has yet caught time breaking its own rules. Experiments with ultra-cold atoms support the idea. In controlled environments, quantum systems can temporarily resist decoherence, their time-reversible behavior preserved like a fly trapped in amber. But introduce even weak noise, an analog for the vacuum's fluctuations, and the arrow of time reasserts itself. It's as if the vacuum enforces a universal statute. Randomness must always increase and the past must stay unchangeable. Yet mysteries linger. If decoherence is driven by the vacuum, why does time's arrow align so perfectly with the universe's expansion? Some cosmologists propose a deeper link, that the vacuum's energy, which fuels cosmic acceleration, also sets the initial low entropy conditions that make time's direction possible. In this view, the Big Bang wasn't just the birth of space and matter, but also the moment the vacuum's quantum dice were loaded, ensuring time would forever flow toward disorder. The implications stretch beyond physics. If the vacuum truly underpins time's irreversibility, it might hold clues about consciousness, why we remember the past but not the future, or even the nature of causality itself. Philosophers have long wondered whether time is an illusion. The vacuum's role suggests it's very real but not fundamental, an emergent property of countless quantum choices, each echoing into the void. So the next time you watch steam rise from a cup or a leaf flutter to the ground, remember, you're not just seeing physics in action. You're witnessing the quantum vacuum quietly, insistently, writing history one irreversible moment at a time. What if the vacuum we perceive isn't the whole story, just a flattened shadow of a far richer, higher-dimensional reality? This is the spine-tingling proposition of Kaluza-Klein theory and string theory, where the quantum vacuum isn't merely a three-dimensional stage but a multidimensional labyrinth, its hidden folds curled up so tightly we've never noticed them. Imagine space as a garden hose. From a distance, it looks like a simple line, but up close, you'd see its circular cross-section, a tiny, curled-up dimension hugging the length you thought was one-dimensional. The vacuum could be doing the same thing, its structure threaded with extra dimensions smaller than an atom's nucleus, shaping the forces we perceive as fundamental. Kaluza-Klein theory, born in the 1920s, was the first bold stroke in this direction. Theodore Kaluza suggested that if Einstein's gravity worked in 5 dimensions instead of 4, the extra dimension's geometry could unify gravity with electromagnetism, as if the vacuum's hidden curls were generating Maxwell's equations like harmonics on a vibrating string. Oscar Klein later calculated that this dimension might be compactified, or rolled up, at scales around 10 to the minus 33 centimeters, far too tiny for any microscope. The idea fizzled without experimental proof, but its legacy ignited string theory's rise, where the vacuum isn't just hiding one extra dimension but 6 or 7, each vibrating at frequencies that dictate particles' properties. String theory paints the vacuum as a cosmic symphony hall. Every particle is a note played on microscopic strings, with the extra dimensions acting as the instrument's body, resonating to produce the masses and charges we observe. The Calabi-Yau manifold, a complex, multidimensional shape smaller than a quark, could be the vacuum's true geometry, its twists and holes determining why an electron has its specific mass or why the Higgs field interacts as it does. In this view, the vacuum's fluctuations aren't just randomness, they're echoes of strings vibrating across dimensions we can't see. But how could dimensions hide so completely? Think of an ant walking on a telephone wire. To the ant, the wire is a one-dimensional path, but to a bird soaring above, it's clearly a thick cylinder. If the ant's universe were scaled down to Planck lengths, it might never perceive the wire's true shape. Similarly, our instruments lack the resolution to detect the vacuum's compactified dimensions, assuming they exist. Some models suggest these dimensions might leak gravity, explaining why it's so weak compared to other forces. If gravity's lines of force extend into extra dimensions, diluting their strength, it would explain why the vacuum seems to mute this force in our 3D slice of reality. Experimentalists aren't leaving this to theory. The Large Hadron Collider once hoped to spot Kaluza-Klein particles, heavy, higher-dimensional echoes of known particles, but found nothing. Yet other approaches persist. Precision measurements of gravity at microscopic scales could reveal deviations from Newton's inverse square law, a smoking gun for extra dimensions. And if the vacuum's hidden geometry influences quantum entanglement, future quantum sensors might detect anomalies in particle correlations that betray higher dimensional links. The wildest implication: if extra dimensions are real, the vacuum might host parallel universes separated not by distance but by dimensional folds. Particles trapped on different branes, short for membranes, in higher dimensional space could be invisible to us yet still tug on our reality via gravity, a possible explanation for dark matter. Or civilizations could thrive in adjacent dimensions, their particles forever oblivious to ours, sharing only the faintest gravitational whisper through the vacuum's multidimensional fabric. Whether fantasy or future fact, these ideas force a humbling realization. The vacuum might be the ultimate hall of mirrors, its true architecture lurking just beyond our perception. And if we ever crack its code, we won't just understand empty space, we'll unlock the blueprint of reality itself. Could the quantum vacuum be secretly guiding life itself? Beneath the complex machinery of cells and organisms lies a layer of physics so delicate, so precise, that it borders on the miraculous, and some scientists suspect the vacuum's fluctuations might be pulling invisible strings in the theater of biology. Take enzymes, nature's microscopic catalysts. These molecular machines speed up chemical reactions by factors of trillions, and for decades their efficiency baffled researchers. Then came a radical idea: what if enzymes harness quantum tunneling, allowing particles to bypass energy barriers like ghosts walking through walls? And what if the vacuum's zero-point energy, those ceaseless quantum jitters, acts as a silent partner, nudging electrons and protons into positions where tunneling becomes possible? The evidence is mounting. Experiments with dehydrogenase enzymes, crucial for metabolizing alcohol, show reaction rates that classical chemistry can't explain. Quantum simulations suggest that the vacuum's fluctuations create fleeting, soft spots in energy barriers, giving particles a probabilistic escape route. It's as if the vacuum whispers to the enzyme's atoms, offering temporary pathways where none should exist. Without this quantum assist, life might grind to a halt or never have started at all. But enzymes are just the beginning. Consider the humble European robin, a bird that migrates thousands of miles with pinpoint accuracy. Unlike humans relying on maps or GPS, robins navigate using Earth's magnetic field. But here's the mystery: the field's strength is 1,000,000 times weaker than a fridge magnet, far too faint for classical biology to detect. Enter quantum coherence, a fragile state where particles remain interconnected across space and time. In the robin's eye, a protein called cryptochrome may exploit this phenomenon. When light hits it, an electron gets kicked into a superposition, two states at once, and the vacuum's fluctuations could help maintain this delicate balance long enough for the Earth's magnetic field to tweak the electron's spin, creating a biological compass needle. The implications are staggering. If the vacuum aids navigation, it means evolution has been quietly exploiting quantum physics for millions of years. Lab experiments with artificially altered magnetic fields show disoriented birds, while quantum dots engineered to mimic cryptochrome respond to magnetism exactly as predicted. The vacuum isn't just empty space, it's a collaborator fine-tuning life's most delicate mechanisms. Dive deeper, and the vacuum's fingerprints appear elsewhere. Photosynthesis, the foundation of Earth's food chain, achieves near-perfect efficiency in transferring energy through plant cells. Classical models predict energy loss as heat, yet plants somehow avoid it. Quantum coherence again provides a clue. The vacuum's fluctuations may help choreograph energy flow through superhighways of entangled states, ensuring sunlight's energy reaches where it's needed without wasteful detours. Experiments with green sulfur bacteria reveal oscillations in energy transfer that match quantum coherence models, suggesting evolution has optimized life to ride the vacuum's quantum waves. Skeptics argue these effects are too fragile for warm, wet biological systems. Quantum states usually collapse in noisy environments, but nature might have found workarounds. Proteins could act as quantum Faraday cages, shielding coherence long enough to matter. Or perhaps the vacuum's fluctuations aren't just noise but a stabilizing force, like a quantum metronome keeping life's processes in rhythm. Either way, the frontier of quantum biology hints that the line between life and the quantum void is far blurrier than we ever imagined. The ultimate question isn't just whether life uses quantum tricks, it's how deeply the vacuum is entangled with life's blueprints. If these speculations hold, the vacuum isn't a passive stage but an active participant in the drama of existence. Its subtle nudges written into the DNA of enzymes, the instincts of birds, and the very leaves on the trees. And if that's true, then understanding life might require us to listen not just to the roar of chemistry, but to the whisper of the void. We've seen how the quantum vacuum shapes everything from particles to galaxies, but what about its final act? The universe's fate might not hinge on colliding stars or dark energy's push, but on the vacuum itself unraveling. Picture this: trillions of years from now, the cosmos could face three possible endings, each more surreal than the last. The first is vacuum decay, a cosmic game of Jenga where one quantum fluctuation too many sends the Higgs field tumbling into a lower energy state. It would start with a single bubble, smaller than an atom, where the laws of physics rewrite themselves. Expanding at light speed, this bubble would erase atoms, stars, and spacetime itself, replacing our universe with something unrecognizable. Terrifyingly, this process could already be underway in some distant galaxy, with the shockwave heading our way. Yet there's a slower, colder alternative: heat death. As the universe expands, galaxies will drift beyond each other's cosmic horizons, their light too stretched to ever reach us again. Stars will burn out, black holes will evaporate via Hawking radiation, and eventually even protons might decay, leaving only a thin soup of particles separated by unimaginable distances. The vacuum would win in the end, its infinite stillness broken only by rare quantum fluctuations so faint they'd make today's virtual particles look like fireworks. Some theories suggest these fluctuations could, over incomprehensible timescales, spawn new universes, a quantum resurrection emerging from the void. Then there's the cyclical model, where the vacuum isn't an end but a reset button. In this scenario, dark energy possibly tied to the vacuum's own energy weakens over time, allowing gravity to pull everything back in a big crunch. The universe collapses to a singularity, only to rebound in another big bang. String theory even proposes that colliding higher-dimensional branes could trigger these cycles, with our 3D universe merely one sheet in a cosmic stack. The vacuum here isn't dying, it's recycling, eternally reincarnating matter and energy in new configurations. The most mind-bending twist: these fates aren't mutually exclusive. Vacuum decay could strike tomorrow, or our universe might already be one of countless bubbles in an eternally inflating multiverse, each with its own destiny. Meanwhile, quantum gravity models hint that near the end of time, the vacuum structure might permit spacetime tunnels connecting dying universes to newborn ones, like cosmic umbilical cords threading through nothingness. What's certain is this: the vacuum holds the hourglass. Whether it shatters it, lets it run empty, or flips it over for another round, we're all just temporary ripples on its infinite surface. And in that uncertainty lies a strange comfort, that even the end of everything might just be a pause in the vacuum's endless, whispering dance. John Wheeler, one of the 20th century's most audacious physicists, once imagined a universe where reality doesn't exist until someone looks at it, where the moon isn't there unless you're watching. It sounds like philosophy, but this radical idea, called the participatory universe, might have roots in the quantum vacuum's strangest behavior. At its core is a haunting question: does consciousness itself play a role in shaping the void? Consider the double-slit experiment, quantum mechanics party trick. When you fire particles like electrons at a barrier with two slits, they create an interference pattern, as if each particle passes through both slits simultaneously, behaving like a wave. But the moment you place a detector to see which slit the electron takes, the interference vanishes. The particle chooses a single path, collapsing from a wave of possibilities into a concrete reality. Now extrapolate this to the vacuum. Its virtual particles flicker in and out of existence in a probabilistic haze until perhaps an observer's measurement pins them down. Could the very act of observation be what solidifies the vacuum's ghostly fluctuations into measurable phenomena? Wheeler took this further with his delayed choice experiment, a cosmic twist on the double slit. Imagine light from a distant quasar bending around a galaxy due to gravitational lensing, creating multiple paths to Earth. By deciding whether to measure which path the light took or its wave-like interference after it's already traveled billions of years, we seemingly influence the photon's decision retroactively. Apply this to the vacuum and you're left with a dizzying possibility that observers today might be sculpting quantum fluctuations that occurred during the Big Bang. The vacuum's history isn't just written, it's being edited in real time. Critics argue this gives consciousness too much credit. The observer effect in quantum mechanics doesn't require a human mind. A camera or even a stray atom interacting with a system can cause collapse. Decoherence theory explains how quantum superpositions dissolve into classical reality through environmental interactions, no sentience needed. Yet some interpretations, like von Neumann-Wigner consciousness collapse, insist that subjective awareness is the ultimate arbiter. The vacuum, in this view, isn't just a quantum soup but a canvas awaiting observation to paint its details. Modern experiments edge toward testing these ideas. Quantum eraser experiments show that erasing measurement data after particles are detected can restore wave-like interference, as if the universe retcons its choices. In quantum optics labs, delayed choice setups with single photons hint that the present can rewrite the past's quantum ambiguities. If scaled up, these effects might reveal whether the vacuum's fluctuations are similarly malleable to observation, a cosmic version of the "if a tree falls in the forest" thought experiment. The implications stagger. If consciousness interacts with the vacuum, could Buddhist meditators or AI systems someday influence quantum probabilities through focused observation? Could the universe's fine-tuning those razor-thin constants allowing life to exist be a self-referential loop where observers guarantee their own existence by collapsing favorable vacuum states? It's a feedback loop worthy of Escher. We're here because the vacuum allowed it, and the vacuum is as it is because we're here to see it. Whether metaphysical or strictly physical, one truth emerges: the quantum vacuum isn't a static backdrop. It's a dynamic interface between possibility and reality, where the act of looking might just be the most powerful force of all. And in that intersection, Wheeler's wildest dream lingers, that we're not just inhabitants of the universe, but its co-creators, whispering shape into the void with every question we ask. After 30 mind-bending mysteries, from zero-point energy's infinite potential to vacuum decay's existential threat, from entangled particles rewriting reality to hidden dimensions curled inside every atom, one truth stands undeniable: the quantum vacuum isn't just the backdrop of reality. It is reality. The void we once called empty is a cosmic hall of mirrors, reflecting questions that blur the line between physics and philosophy. Does the vacuum compute? Does it remember? Could it even think? The answers might not just redefine science, they could rewrite what it means to exist. Think back to the Casimir effect's invisible push, sonoluminescence turning sound into light, or actions hiding in the vacuum's folds as dark matter. Each revelation peels back another layer of the universe's greatest magic trick, that nothingness is never truly nothing. The vacuum breathes, fluctuates, and perhaps even evolves. It's the reason particles have mass, black holes glow, and time marches forward. It might be the scaffold of consciousness itself, or the graveyard where universes go to die. But here's the kicker, we've barely scratched the surface. For every mystery solved like the lamb shifts proof of virtual particles, a dozen more erupt. Why does the vacuum's energy not rip spacetime apart? Are we living in a hologram projected from its depths? Could a false vacuum bubble already be racing toward us at light speed? The more we learn, the stranger the questions become. This isn't just science, it's the ultimate existential detective story, and you're part of it. So tell us, which of these 30 vacuum mysteries unsettles you the most? Is it the phantom particles flickering in and out of existence? The chilling possibility that dark energy is the vacuum slowly tearing reality apart? Or the spine-tingling idea that observation itself might shape the void? Drop your thoughts below. We're obsessed with these cosmic riddles, and your perspective might just spark the next breakthrough. If your brain's buzzing from this quantum journey, you're not alone. Hit subscribe and tap that bell. We've got even wilder cosmic deep dives coming, from time loops to white holes to the quantum roots of consciousness. The universe's weirdest secrets are waiting, and the vacuum's whispers are just getting louder. Ready to dive deeper, the void has answers. Let's find